Hello to everyone. I am Nicola Davanzo from the Laboratorio di Informatica Musicale, or Laboratory of Music Informatics, from the University of Milan in Italy. And my work is Headbower, an experimentation towards expressive violin control for musicians with quadriplegia. The intention behind this work is very simple. Music makes our life beautiful, and playing music gives us expression. The psychological effects of playing music are well known, as well as the need for a sense of participation and taking part in our communities. But some people, as we know, still cannot access it. They're probably, in my opinion, missing the voices of a minority. What will they tell us if they are able to express artistically? And the main reason behind the commitment into researching hands-free, accessible digital musical instruments is that conventional instruments are mostly meant to be played through hands. So people with quadriplegia, hand impairments, amyotrophic lateral sclerosis in advanced stages, for example, have few or no possibilities to get into music performance. So how do we achieve hands-free musical interaction? In the state of the art, the most common technique is eye tracking, specifically gaze tracking. We find many gaze-based instruments. iHarp is probably the most famous. In our laboratory, we developed some prototypes like Meditar, and again, most of them are gaze-based. Using these instruments, we can play melodies, chords, or with all kind of different visual systems and layouts. And we are slowly getting some insights into ways to overcome the limitations of gaze-based interaction. So we have instruments that we can use to play melodies and chords. We have also an interface for DJing, but a few of them go after the note and chord selection and note intensity choice. Basically, they offer no control over timbre, envelope, and other expressivity parameters. So we wanted to try to perfect this art and try to enhance the expressive possibilities of the instruments to achieve more personality, more musical personality. So here comes our new experiment called Headbower, which is both an instrument prototype, but is particularly meant to be a collection of interaction experiments. Maybe the most important concept, the core concept behind Headbower, is to try to translate head movements into the gesture of violin bowing. So let's find out how Headbower was actually implemented. Headbower was developed using C#, in particular the Windows Presentation Foundation graphical framework for the development of graphical user interfaces, and the NEAT framework, which is a framework that we developed at the Laboratory of Music Informatics. The NEAT framework is an ecosystem that we are developing for fast prototyping hands-free interaction solutions, trying to make things open source, affordable, and customizable, and adhering to a philosophy which is very popular in the world of computer science, which is KISS, or keep it simple, stupid. And the NEAT framework includes libraries and sensor devices that you can replicate through do-it-yourself practices for wrappers, software wrappers to make already available ones compatible, and development and testing tools and facilities. The ideal objective that we want to achieve and that we are working on with the NEAT framework is to map every interaction channel that is available to a quadriplegic person and to provide the sensors or the tools to use all of them basically and to develop application using all of them. So for example, to use eye motion, voice qualities, mouth aperture, feet pressure, even the tongue movement and head rotation. And why not many others that we may discover in the way. So let's see how Headbower works, starting from sound generation. Headbower is a MIDI controller, so it's a mute interface. It can work with many synthesizers, but we designed it having in mind the Swan Viola from audio modeling. It's our default engine for sound production. The Swan Viola is based on a physical model of the instrument, so we have many parameters to control. The most important ones for Headbower are a realistic bowing gesture simulation and bow lift. The basic idea behind Headbower is to use head rotation as a main source of interaction. More specifically, the head rotation along the yaw axis actually mimics the gesture of the bowing hand on the violin. So we have the rotation along the yaw axis that control bow sweep and intensity, while, of course, directional changes will trigger not on and not off events. All the other two axes are used to trigger many other kind of effects, such as vibrato, pitch bend, and to control the bow pressure. And these are basically switchable in the Headbower settings interface. We provided three main sources for head tracking, which are all included in the NIF framework. We can change the source of head tracking data at runtime. The first one is the NIF webcam wrapper, which is using webcam for head tracking. The second one is NIF phone wrapper, using a smartphone accelerometer for head tracking. And the third one, which is the most precise one, is the NIF head tracker, which is a hardware head tracker built using Arduino and a high-performance accelerometer and gyroscope chip. In Headbower, note selection is achieved in a very classical way in the world of hands-free interaction, which is through gaze tracking. The musician simply has to gaze to a note button in order to trigger the selection of that specific note and to play it. When designing gaze-based interfaces, there is a big problem to take into account that's called Midas touch, which is a classical problem, actually. It's easy to explain. Take into account, for example, this piano keyboard layout that you can see in the middle of this slide. If we have our eyes, our eye gaze on the C key, and we want to change to the A key, so we look at the A key, even if the eyes move in a really fast and jittery fashion, all the keys in between may be detected because eye trackers are very fast to track our eyes, and the result will be dramatic because all the notes in between will be played. So many accessible digital musical interfaces experimented with different layouts. In Headbower, we introduced two new solutions, which are a violin neck layout, which may be intuitive for users with prior musical experience. For example, users who played the violin during their life and maybe lost their control over their hands because of an accident, or a spinal cord injury, or anything else. And this layout could be also useful to exploit the available repertoire for the violin. And we will see how Midas touch is minimized also in this layout. And the other one is a circular layout using a novel design, which is particularly studied to minimize the Midas touch problem. So this is the Headbower in the violin layout configuration. And as you can see, I am playing it through a subtle yaw sweep motion. And I am controlling the vibrato with the mouth aperture. So, as we saw in the video, a new note is triggered when the gaze moves to the next key, but this is not sufficient because we also have to change the direction of bowing. So we have to change the direction of our head rotation from left to right or from right to left. So in this way, even if we gaze at intermediate keys, they are not triggered until the bow direction is changed. While the Violin layout may be interesting for knowledge transfer, the circular layout that you're seeing right now is studied for gaze interaction. As you can see, the gaze key goes to the center, as this allows me to do not cross intermediate keys. And I can follow this motion with my eyes because of these multiple suite capabilities of human eyes. As we mentioned in the beginning, one of the main ideas behind the Headbower is to achieve expressive control over the violin synthesizer. So we control two main parameters for this synthesizer, which are bow lift and vibrato. Bow lift is actually the pressure on the strings, and vibrato is actually MIDI modulation. In the settings panel, you can select which source is mapped to the bow lift and which one is mapped to the modulation. So you can use mouth aperture, which is mapped through the knit weapon wrapper, and jaw pressure through the knit bite sensor, for example, or head rotation parameters, which are pitch and roll. Another idea that was included in Headbower is to try to provide haptic feedback through the phone's vibration actuators. So we developed an application called Knit Phone Wrapper, which is a companion app for Android that basically makes the phone vibrate on the bowing gesture. The idea is to place the smartphone on the sensitive part of the musician, such as the neck, for example. So Headbower in its current state is a functioning prototype, template, but most of everything is intended as a collection of ideas, a creative showcase, a starting point to be expanded and to be refined, to see which of the implemented ideas is actually most suited and in which cases. It needs testing on the field, but I can offer some preliminary observations by the author. I feel that the head bowing metaphor is intuitive. The circular layout feels effective and error-reducing, especially if compared to other solutions and other layouts. Should be investigated. The smartphone delivered haptics seems to introduce more immersivity, and this also should be investigated. Also, it has to be investigated a compromise on head angle, which enables gaze tracking, because if you tilt your head to match the head trackers start to not detect you. I know that many ideas have been brought to the table, and the demo video is absolutely sufficient to give an idea on how all of them work. The Headbower is open source. I invite you to just download and test it. In order to do so, we'll need an eye tracker able to control the mouse cursor through gaze, but you can just try it with a mouse. We'll need a webcam for head tracking, and you can use the Knit Webcam Wrapper that it's a Python application. And the prototype actually works only on Windows operating systems. You can download it using the link on GitHub that you'll find below. And you can also use the QR code that you'll find on the right side of the screen. Thank you for your attention, and I hope to have brought some inspiration to all of you.